Good morning, everyone, and good evening in other place. We will start the second lecture of Raghu Mahajan from Stanford. Today he will teach the non-zero temperature island and the entropy paradox for the eternal black hole.
Yeah.
Please.
Okay, thanks, guys. We'll do just a very quick recap of last time, and then go ahead, and then maybe after the recap, we'll stop for questions just to finish the zero temperature story. Okay, so what we are trying to do in order to resolve the information loss paradox is that we are trying to compute entanglement wedges and entropies of the radiation region of evaporating black hole. So entanglement wedge and entropy. So both of these of a boundary subregion, we said are computed by the quantum extremal surface formula in which we minimize the generalized entropy. And the generalized entropy definition is that it's the area of the surface of the candidate Ryuta-Yanagi surface or a QES surface divided by 4G, but importantly has the S bulk term between S bulk of the matter between the QES and the boundary region. And in 2D gravity, the area got replaced by the value of the dilaton over 4G plus S bulk. And we started putting this formula to use in sort of a very simple situation. We have a SYK model that is time. So there's a boundary theory, which is 0 plus 1 dimensional in its zero temperature ground state. And it's dual to a zero temperature ADS2 geometry. That is the Poincare patch. And we computed the entanglement wedge of the whole boundary. And if the ADS-CFT duality is true, the entanglement wedge of the whole boundary should be the whole bulk Cauchy slice. Cauchy slice. So if we call this point O, then the quantum extremal surface was at the point Q, all the way at the Poincare horizon, and the entanglement wedge was OQ. And the way we did that was that the S-gen at candidate point, let's call it P, S-gen as a function of P was phi plus S bulk. And we saw that phi was phi r divided by A, plus there was only one contribution from the matter because the space has a boundary and the left and right movers are not independent. But then this position dependence was canceled by the Vial factor in the metric. And so the extremization, the value of A star, happened at infinity, which is all the way to the Poincare horizon. And then in order to build up to an evaporating black hole, we took the SYK model, coupled it to a wire. So this wire is supposed to represent some heat path that is supposed to take away the energy of a black hole. And again, there is time. And we said that the dual of this system is the ADS2 Poincare patch, but now glued to a flat space region. This is flat, this is ADS. And the only difference from before is that the joint system is in the t equal to 0 ground state. So there is some entanglement between the SYK dot and the wire. And so the entanglement wedges and the entropies get shuffled around. And importantly, in the bulk, the matter fields have transparent boundary conditions rather than reflecting boundary conditions. And what we set out to do was to compute the entropy and entanglement wedge of the black hole region. And we expect that the black hole is mostly made up of this SYK degrees of freedom, and the wire just represents some Hawking radiation. So we try to compute the entanglement wedge of this system here. And okay, so we again make first a candidate quantum extremal surface Q. There is the point O here, and OQ is a candidate entanglement wedge. And what we want to do is call the coordinate of Q as negative A. And this is, of course, at 0. And then we wanted to compute Sgen of A. And that was equal to phi r over A from the dilaton plus C over 6 times log A, but now multiplied by 2 because left and right movers are independent, and then negative C over 6 log A from the Vial factor. And that gave us phi r over A plus C over 6 log A. And to find the QES, we are supposed to take DDA and set it to 0, which gives 0 equals negative phi r over A squared plus C over 6A. And this gives A star equals phi r times 6 over C. So it's not infinite. And it's some finite value with the length scale set by this phi r, which is a dimensionful parameter of JT gravity. So what we find is that the SYK without the wire is dual to only part of the ADS2 spacetime. And the wire is just the wire. And now our entanglement wedge, let me draw it in red. So this is the red region. And the part of the bulk spacetime that's dual to the SYK is just some finite piece with a point Q, where the coordinate of Q lies at t equals 0, is z equals negative phi r 6 over C. Okay, so this is where we were last time. And we have a quantum extremal surface corresponding to the SYK, or the black hole degrees of freedom. Okay, is there any question about this?
I have a question. So
Yes.
here SYK is 0 temperature and Beth is also 0 temperature. So naively
Yeah,
sounds
they are
like they
coupled.
will, yeah, coupled and at 0 temperature. Will
Yeah.
there be some Hawking radiation or just
No. So this case
equilibrium?
is just a warm up. There is no Hawking radiation here. And we are just doing this as a calculation, like just warming up about these generalized entropy calculations and
Okay.
extremizing them.
Okay.
Yeah, so it's just a warm up to the finite temperature case. But there is already a very surprising thing here, which I'm going to present next. But before that, let me ask if there are any questions, any other questions. Okay, so the real merit of this problem is not this, but let's look at the complement system. So if we have the SYK, this coupled to a wire, we can ask what is the entanglement wedge of the complement? And let me draw that in blue here. So what's the entanglement wedge of the blue region? The point is, since the red plus the blue, the SYK plus the wire is dual to the whole system, the entanglement wedge of the blue region should be the complement of the red entanglement wedge that I've drawn here. Okay, just because the full boundary has to be dual to the full bulk. So we should have that, the entanglement wedge of the blue region is somehow this blue plus this blue. It has to fill up the Cauchy slice. So I'm just going to redraw this here, just the blue regions. So we have the Poincare patch, and we have this. And now on it, we have an entanglement wedge that has two disconnected components. There is this piece, and there is this piece. And this is what we really want to compute, because in a page curve, we want to compute the entropy of the radiation. And the wire is the radiation region. So what we find is that the entanglement wedge of the radiation region is not just so this we could call the naive, what we might have naively expected. Because remember, the wire, this part of space is completely flat and not just flat, it doesn't have gravity, no gravity. So you might have thought that its entanglement wedge is just the causal wedge. So this is the naive, what you might call the causal wedge. But what we have found is, no, it's not really true. This is not the full entanglement wedge. The entanglement wedge is the union of the radiation now, of the wire or wire, is the union of the causal wedge, the naive thing, plus an island deep in the gravity region. Okay. So that's what this means. So yeah. Is this argument clear? Just from the taking complements in this picture above. And this is the simplest example of how the quantum extremal surface formula can spring a surprise. And there are other situations in ADS-CFT known when the entanglement wedge is bigger than the causal wedge. But this one is particularly useful for understanding the black hole information paradox. And this is an indication, and there have been indications all along that gravity has non-local effects. So there are no naive violations of causality, but the point is that the true radiation region, which lives here in the wire description, nucleates two separate regions in the space-time. This also means that if you were trying to do bulk reconstruction, like along the lines of the HKLL formula, or trying to figure out, okay, let's say I created some particle here. I'm a bulk guy and I create a green particle here. What does it look like in the dual, on the dual side? So remember, SYK plus wire is really the dual side. It basically corresponds to the same particle, maybe a little distorted in the wire. So this corresponds to the fact that if you have an operator in the causal wedge, its reconstruction on the boundary is very simple, is not very different from what it is in the bulk. But if, on the other hand, you put a particle on the island, which is a part of the entanglement wedge, which is not in the causal wedge, its reconstruction is completely crazy. You have to use either some modular flow or something. And so, yeah, so simple operators in the entanglement wedge, even simple operators in this island region, are very, very complicated messes in the actual dual description. So that's the difference between the two. But it's there and it's real.
Is there some physical intuition why this wedge appear in the deep in the gravity side like
Right. So the intuition is from the black hole evaporation. So as a black hole is evaporating, we build up this entanglement between the interior of the black hole and the radiation. And the point is that, yeah, there is a lot of entanglement built up between the interior of the black hole and the radiation. And by including this island, in your region of interest, you reduce the term S bulk, because now both partners of an EPR pair are in your region. So they don't contribute to the S bulk term. So what this is representing is really some entanglement pattern of the state we are considering.
So I mean, I'm asking the position why it's really deep in the bulk, not the near the, for example, naively one can say that it appear in the also wedge can appear in the near this boundary, but here it's very deep in the near the horizon.
Yeah.
So is there some way to
I think
understand it?
Yeah, the idea why it shouldn't appear near the boundary is maybe the picture above. So since the SYK dot is really, morally it sort of lives at the boundary. So the space near the boundary should be created by the SYK.
Okay.
Because there you have some UV physics, right? This is sort of this system. This is really living, at the boundary here. So this is like if you said that the SYK and you bring in the wire, right? You're maybe doing some RG flow from the ground state of SYK to the ground state of the total system. And when we do such RG flows, it's the deep IR that changes. The UV properties remain the same, roughly speaking.
I see.
So that's maybe another intuition. But
Okay.
I should say that this is really the output of some calculation.
Okay.
We did the calculation here. We found this extremal surface point Q. Okay. Thanks for the questions. Please ask. This sort of sets up, some sort of a feedback loop, so I know that I'm not just talking to a blank screen.
Could you please say
I ask a question?
Yes, please.
Bulk causality. Well, basically the information contained in the island violate bulk causality. So the bulk causality is not strictly physical in a certain sense.
Yes, exactly. That's true. And but you see from this picture, it's clear that to detect those violations of causality, you would have to do some very complicated operations. Because the commutator that will detect, so if you want to compute the commutator of the two green blobs that I drew here, like this one and this one, it would sort of be the commutator between a simple operator here and a very complex operator on the wire. And that would be a very small commutator, but it will be non-zero in general. And so one way to say it is in a relativistic QFT, or just without gravity, we associate operator algebras to causal diamonds. Whenever we have a causal diamond, we say there's an independent operator algebra that lives in this region. What the QES is telling us is this picture with the blue is telling us that the operator algebra that we should associate is not just to the naive causal wedge, but to the union of the two. That it's only the union of the island and the causal wedge to which we should attach some operator algebra. Right, and we know that bulk causality, can be violated because just in gravity, geometry is fluctuating. So strictly speaking, the notion of 2 points being space-like or time-like separated is not well defined in the bulk.
So so this violation of causality is also true in our universe where we have gravity. So that seems too much.
Well, I would say that, for example, it's true in this case that, let me redraw the figure here. And I want to emphasize this is not a very radical statement. It's a simple statement, which is saying that, for example, if you take this here, you take this green thing that I drew here, and you do a modular flow of this, operator. You might have thought that the modular flow keeps you within this diamond because of light cone, but in a very nice paper, assuming the entanglement wedge reconstruction, Yiming Chen showed that, for example, that once you do modular flow, it immediately sort of appears here. There's like the operator under modular flow becomes supported on both of those regions. Now, but I want to emphasize this is not a very drastic statement because to detect it, you would need to do experiments that are accurate to like e to the minus the entropy of the system. Like these are effects that are sort of highly suppressed in G Newton. So we expect that for, yeah.
I see. So basically difficulty in experimental observation is a sort of protecting usual sense of causality. That is what.
Yes. Yeah.
Okay.
It's like it's only for simple observers because we do simple experiments and so on. But I want to emphasize that the notion of locality, is that we learn in QFT is something like operator at X and operator at Y is 0 when X and Y are space-like separated. But if in our universe we have active gravity and G Newton is non-zero, just the metric fluctuates. So, we can have an extremely large fluctuation in the functional integral in which x and y, the 2 points that you thought you were monitoring, become now time-like separated. So since the very notion of space-like or time-like depends on the metric, and the metric is an integration variable in quantum gravity, the strict notion of causality we should not expect to be true in any sort of reasonable theory of quantum gravity under non-perturbative effects.
Okay, thanks.
Okay, thanks for the question. Okay, are there any other? Yes.
Can I ask one question? So can you give us a simple example where the local about the local operator inside an island that maps to the operators in on the wire?
Yeah, this would be it would have to be some sort of implicit answer. So if entanglement wedge reconstruction is true, then you could follow, for example, this paper of, and we believe it's true, you can follow the paper of Faulkner and Lukowitz to write down the, it will have to be like a bit abstract and not abstract, it will be an explicit formula, but it will involve some modular flow in which there will be a modular Hamiltonian, which will not be very explicit, except in very simple situations. So just the entanglement wedge reconstruction formula should hold here. And also, I should say, there's not just modular flow, but people have also discussed the so-called PETS map reconstruction. So there's yet another thing you can write down, which would achieve this. And in this PSSY paper by Pennington, Saad, Schenker, and Stanford, in even a simpler toy model, they showed how it works. So there's this PETS map object from quantum information theory. But it's again complicated. The PETS map is complicated, the modular flow is complicated, and so on.
I see. All right, thank you.
Yeah. Okay, great.
Can you quickly
Yes.
tell? So what happens if the blue region is the whole wire? I mean the.
Yeah. I meant it here to be the whole wire. Yeah.
But then in that case, why is it?
It's still like I was going to do the generalization now, but yeah, that's the surprising thing about this. Again, you're asking exactly the right question. You would have thought the SYK is responsible for creating the ADS2 and the wire is just the wire, but it's not true. Like after they interact, they're in a combined ground state of the total interacting system. It's just a fact that the SYK fermions are responsible for creating only a part of the space-time, the gravitating space-time.
So what region of the SYK plus wire should I consider so that the entanglement, the blue region on the right-hand side becomes the whole, you see, the whole Cauchy surface?
Sorry, maybe I should just redraw that figure since I messed it up. So let's take the SYK plus the wire, and let's put our partition right here, right at the boundary. And this is our blue thing, right? And we go here, we draw this, and then the blue is like that and like that. This is what I should have drawn.
Oh, I see. So that's okay. That's exactly okay. Good. Right.
Is that what you were asking?
Yeah.
Okay. Yeah.
Okay.
Sorry. Yes.
So is there any region for SYK plus what the wire such that you don't have an island on the left-hand side? I mean the island?
Yeah, you can play some games like Rob Myers has a paper showing that you start taking some sort of several disconnected intervals in the wire, and you can play around with that, but I don't want to go in that direction.
So it's not going to tell us something more intuitively, something, in fact, this is already very counterintuitive.
Yeah. Yeah. The idea is just to have the simplest situation where we have this kind of non-locality or an island sort of show up, and then just go ahead to the, the finite temperature case.
All right, thank you.
Okay. All right, so let's move on and go to the, the finite temperature story. Okay. Non-zero temperature, and we will have a black hole. But we will not have an evaporating black hole, we will have an eternal black hole. But there will still be an information paradox in the eternal black hole, and we will still resolve it using a non-trivial quantum extremal surface or with islands. Okay, so what is the setup? Okay, we have now an SYK again, okay, plus the wire. But now we put the combined system in the thermal density matrix, e to the minus beta h total with some beta. So it's in a mixed state, it's in a thermal state. That's fine. And h total just means HSYK plus S wire plus maybe some local interaction term where you have them joined. Now, any system such as quantum system, if it's in a mixed state, has a purification. So we introduce its purifying system. So this is the purifying left system. And the combined system is in the thermophile double state, right? So the usual. So now we have two SYKs and we have two wires. And now the total system is in a pure state, is in the thermophile double state. Okay, so this is our system, a non-gravitational description of the system. We want to now first just say once and for all, what is the region whose entropy we are going to compute? And the region is going to be like the wire region, but we are going to take the wire and sort of its partner on the left-hand side. Okay, so the region A is going to be the left wire plus the right wire. So if you imagine the thermophile double Penrose diagram, you're taking some region far away on the left and union the region far away on the right. Okay, and okay, so that's some entropy. It will have some entropy, but we want to compute some entropy as a function of time. And for that, we introduce sort of time dependence into the game following Hartmann and Maldacena. So Hartmann and Maldacena studied a very simple example of a situation when the entropy is time dependent. So just let's recall that quickly. So any thermophile double state is a sum over energy levels, e to the minus beta En over 2, n left and right. I'm not normalizing the state. Okay, and this has the property that h left minus h right acting on the thermophile double state is 0. It just annihilates the state, as we can see just by, it's more or less obvious from the above equation. But h left plus h right on the thermophile double is not 0. So this sort of corresponds to the boost symmetry of the thermophile double. And what the next line says is if you move the time up on the left and the right, then it's not a symmetry. So if we evolve the state using this Hamiltonian, which is the natural Hamiltonian from the boundary point of view, then we just get some time-dependent state. This is a time-dependent state. And the time parameter is here. So all we want to do is having the region A being defined above and the time evolution being defined like this. We want to compute S of A as a function of time. This is our goal. Okay, so basically the thermophile double state from the point of view of h left plus h right is a high energy state. So that means that the expectation value of h left plus h right in the thermophile double state is just like some has macroscopic energy. Okay, and furthermore, whenever we have such states which are not eigenstates of the Hamiltonian, the entropies of subregions grow linearly in time. This is for people familiar with the quantum spin chains. This is like the situation like in a quantum quench. Basically, generically, entropies of subregions grow linearly in time. And this is indeed what will happen, and this is what indeed Hartmann and Maldacena had studied in the thermophile double. Okay, so we have a entropy which is growing linearly in time. We will compute it later, like what the precise coefficient is of this linear growth. But the point is it's growing linearly in time. So let me draw here the system again. We had our two SYKs. We had these wires. And we are computing the entropy of this region A, this thing, right? And it's growing linearly in time. So what might you draw as the curve? So here is time. Okay, here is S of A as a function of t. And you can draw a straight line, roughly speaking. But you know, S of A has to be equal to S of A complement just by purity, because the total system left plus right is in a pure state. Sorry, I should write this properly. So S of A equals S of A complement. But what is what is A complement? A complement is just a bunch of finite number of fermions. Or in other words, S of A complement is less than or equal to the Bekenstein-Hawking entropy of the black hole. Right? If this SYK is sort of in a finite temperature state, it's dual to a black hole, and there's a factor of 2 because there's 2 of these guys. So it can't be that this linear growth lasts forever, because the complement, the black hole, has an entropy which is bounded by its Bekenstein-Hawking entropy. So something has to come in and flatten this curve out at late enough times. So we will call this the first phase, the phase of linear growth, which is true at early times. And then at late times, it sort of saturates. If it was an evaporating black hole, it would go down. But in our case, we are studying an eternal black hole, and we would have this kind of a curve. And again, how the curve transitions from 1 to 2 is that there will be a competition between two quantum extremal surfaces. This would be the naive quantum extremal surface, having just the causal wedge of the radiation, just causal wedge, and then at some point it just loses. Its generalized entropy is larger than a new quantum extremal surface, which has already appeared before, but it's not dominating at the time. So the goal of the rest of the lecture, and maybe part of the next lecture, is to compute in detail the entropy of 1 and the curves 1 and 2, and just go through it in JT gravity coupled to a CFT. And of course, this is the page curve in this situation. Okay, is the setup clear of what we are going to study?
Can I ask you something?
Yes.
For the complement of A, you're saying is 2 SYKs, but is it
Yes.
obvious that once you evolve that state with HL plus HR,
Yeah.
then the entropy is still equal to the black hole entropy?
Yes, because if we have n fermions, just the dimension, so the entropy can never be larger than the entropy, than the log of the dimension of the Hilbert space. And since fermions have a finite dimensional Hilbert space, essentially it's upper bounded by that. And in the black hole case, it's also true that if a black hole is not evaporating, it has a finite area which is not changing. This entropy is just upper bounded by that. I mean, the time evolution doesn't come into a bound on the entropy. This bound is like how much Hilbert space you have, how many independent vectors in the Hilbert space you have.
Okay.
The vector can evolve in time in Hilbert space however it wants.
Okay, yeah. Thanks.
Okay, great. All right, other questions about the setup? Okay, so let's go ahead and compute first the curve one, the linearly growing phase. And I'm going to call this coordinate here B. So this is at the origin, and this will be called B, where the wire starts. We can set B to 0, but it's helpful to keep it general, keep B general. So B will be a number which is greater than 0. Okay. So to get some intuition, let's draw the Penrose diagram of what this thing sort of looks like. So we have these two SYKs, and keep drawing that again and again. We have these two wires. And now the ADS region is like a black hole. It has a Rindler kind of structure. And you might say Rindler coordinates are just some coordinates. What does it matter? But the point is the dilaton profile is different, that there is a singularity that comes in here. So we can't really change it. And it's a time-like singularity. And then we have these flat space regions that are glued on. Okay. So this is the heat path on the right. This is the heat path on the left. No gravity here. And this is the bifurcate horizon. We have a black hole. A crucial role is going to be played by sort of this diamond here, this big diamond here. And I'm going to just number these things. So let's call it left, right, top, and bottom. So the LTRB square will be important. Okay. And since the initial part, we don't have a non-trivial quantum extremal surface, and we're only computing the entropy of some region in a field theory, the gravity essentially plays no role. The gravity plays no role, so we can just forget about the JT gravity for now and just ask what's the entropy in a QFT of a region like we have picked. So what is the region we have picked? From the, okay, so let me draw now. Of course, this was a Penrose diagram, right? And we have this point B here. So what does it correspond to? So now I'm just ignoring all the gravity stuff, and there is left, top, right, and bottom, and we have this decomposition here. So this is nothing but the Rindler decomposition of Minkowski space. So we have a right Rindler patch, we have a left Rindler patch, and we have the future and the bottom regions. This point B, essentially, since we were evolving the state by e to the negative IT, h left plus h right. What we end up doing is moving this B point on these constant Rindler spatial coordinate curves. So we move them up. So the region A, the blue region, is sort of this thing plus this thing. So that's like region A. And we move the tip sort of forwards in time along a hyperbolic trajectory. Constant Rindler spatial coordinate. And the idea is to compute the entropy of the union of the two blue lines. Okay, so let me redraw this figure now to make the answer more intuitive. So let's forget about this Penrose business because it distorts distances, and let's just draw it in usual coordinates. So we have here Minkowski time, we have here Minkowski space, we have here the Rindler horizons, right? And we are moving along some hyperbolic trajectory at constant b. So this is b, this point is b here. And okay, we have this point here and the point here, which are being moved along. Okay, now, of course, the entropy of the union of the two blue things by purity, right, is equal to the entropy of this interval. So the entropy we are looking for is equal to the entropy, let me call now this point P and this point Q, is equal to S of PQ, just because the global state, again, is pure. But as you're moving them along the hyperbolic trajectory, what's happening to the length of PQ? The length of PQ is growing exponentially. Right, just because of the nature of the trajectories on which the points P and Q are being moved. So the entropy, which is like log of the length, grows linearly in time. This is basically the Maldacena-Hartmann argument, in which this length of the PQ is growing very fast. It's sort of the slice that goes in the inside is growing very fast. And yeah, this is not precisely the Hartmann-Maldacena statement, but it's sort of morally similar to that. Okay, and now we will compute the exact number, like what is this entropy? Okay, is the picture clear? Okay, so now we will just set up the coordinates and do the computation. Okay, so now I'm just going to draw the light cone coordinates. This is plus, this is minus. So the Minkowski coordinates I'm going to call x plus and x minus. The Rindler coordinates I'm going to call y plus and y minus, right? And we have here this trajectory. Let me just focus on this point, which I was calling Q. So what's the relation between x plus and y plus and x minus and y minus? So x plus is only a function of y plus. And let's focus on the right Rindler patch. So in this patch. So in this patch, x plus is positive. So it's positive. So I may write it as e to the y plus. So as y plus spans the entire real line, x plus only goes over the positive real line. X minus is negative in this quadrant because the origin is here, and here x minus is negative. So it needs an overall minus sign, and it needs an e to the y minus, but you put a minus sign here so that x minus and y minus increase together. It's not like if y minus increases, x minus should decrease. They should both increase or both decrease. So this is the Minkowski to Rindler map between x plus and y plus, and x minus and y minus. It's just simple to write in light cone coordinates because it's just a function of one variable. Okay, so now let's just write the coordinates of Q. So the t comma y coordinates are t comma b. So y plus and y minus are like t plus b and t minus b. So x plus and x minus are the exponential. So e to the t plus b minus e to the negative t plus b. Okay, so these are the x minus and x plus coordinates of the point Q. So this is Rindler light cone, and then Minkowski light cone coordinates. And the point P here is located symmetrically with respect to the vertical line in this diagram. And the vertical line has the equation x plus equals x minus. So this line here is x plus equals x minus. And when we reflect a point in that line, we just end up interchanging the x and y coordinates. So the point P has x plus and x minus coordinates. We just have to swap these. So it will be negative e to the negative t plus b and e to the t plus b. So this is the point Q, this is the point P. And we just computed their coordinates. Okay, that's fine. So let's compute the delta x plus, that's the next step. So delta x plus is the difference in the first coordinates. That's e to the b times 2 cos t. And delta x minus is e to the b times 2 cos t again. Okay. And we just see that now if we do c over 6 log of delta x plus, we're going to get log of a cosh. And log of cosh at large times is linear in time. But there is one thing we have to be careful about, which is the following. What is the metric on our space? What is the metric? So if we go back here, right, we are really interested in the black hole situation. And the physical bath region lives in this flat metric in the y coordinate. So really the ds squared is negative dy plus dy minus. Because this big rectangle that I drew, this LTRB, is just some fake thing. This doesn't exist. The real actual system just lives on this half space, in flat half space. Okay, so this is the physical metric that we're supposed to work in. But what have we here? So ds square is negative dy plus dy minus. And remember, y plus was e to the y plus was x plus, and x minus was negative e to the negative y minus. So this is just negative dx plus dx minus divided by negative x plus x minus, right? It's the log, so y plus is like log of x plus. So we get this. So actually, it's convenient to work in the x coordinates because we fit both of those left and right things together, and that's where the interval PQ lives. But we have a non-trivial Vial factor. So the Vial factor here is basically negative x plus x minus to the 1/2. Right? Remember, we defined our metric to be negative omega to the negative 2 dx plus dx minus. So we have to remember the Vial factor. We can't ignore it. Okay, that's fine. So it's just x plus x minus to the 1/2. We had it here, right? We have the points P and Q. So we can compute omega at point P. The T cancels. When we take the product of x plus and x minus, the T cancels. It's e to the b, which is also equal to omega of Q. So this information, together with this information, is all we need to compute the entropy. So yeah, let me just take this stuff. Put it here. And then we can just compute S of PQ, which was equal to S of A, equals C over 6 log of e to the b times 2 cos t times 2 minus C over 6 log of this omega stuff, e to the b, but again times 2 because there are 2 of them. Okay, so we just get C over 3 log of 2 cos t. And for t much bigger than 1, that's the temperature. So this is really t much bigger than beta. This is like C over 3 times t. So this is the phase 1 of the page curve. And notice that there was no quantum extremal surface involved, blah, blah, blah. So what that means is that, if you were to draw now this Penrose diagram, you have these Rindler horizons, we have the flat space here, that the entanglement wedge is just the naive one. It's just this blue plus this blue, and that's it. This is B, this is B. The gravity region just does nothing. This is like, before the page time for an evaporating black hole, Hawking's calculation is actually correct. And we do have an entropy of the radiation, which is growing linearly in time. Are there any questions about this? Okay. Yoongi, am I going too fast, too slow? What's the?
To me it's okay, but I a bit worry about the student. But
Okay, maybe I should slow down then a bit. That's,
yes.
Okay.
Okay.
Okay, so maybe I can summarize. So we want to model a black hole, which is an eternal black hole. We have an SYK. We couple it to a wire to model the Hawking radiation region. This is in a thermal density matrix. But so then we introduce a purification system here. The Penrose diagram of this thing is like the eternal black hole, something like this. And our radiation region, capital A, is like some radiation region on the left, and union, the same thing, union its partner on the right. And the time evolution we are doing is evolving both sides forward in time. Which is not a symmetry of this diagram. If we evolve the left forwards and the right backwards, we would have a symmetry. It's a boost symmetry of this thing, but this is not a symmetry. And then we found that SA of t is basically linear in time. And the way we did that, this computation is a purely CFT computation with no gravity. And the essential moral why it was growing linearly in time is because just of the locus here. We have some kind of Rindler space, and the entropy of the region A is equal to the entropy of this interval PQ. And the length of PQ is growing exponentially in time, just because these hyperbolas deviate from each other exponentially in time. And in a 2D CFT, the entropy of an interval is log of its length. So if its length is growing exponentially in time, its entropy is growing linearly in time. And that's the initial part of the page curve.
Can we see in this case that geometrically how SA equals SA complement?
You mean because it's infinite, the A complement is infinite?
Well, no,
Sorry,
I thought
maybe I didn't. What do you mean by seeing it geometrically?
See, you did a purely CFT calculation, and A was a region, the wire region, right, on both the sides.
Yes, it was this P to negative infinity and Q to infinity. Yeah.
Yeah. So now A complement is then basically SYK plus whatever regional wire if you want, or just SYK.
Okay. Sorry. Yeah. Sorry. I did this. So I said this quickly here, but when I said that in this initial phase of the computation, the gravity is not important, that means we can forget about this SYK business. Like if we look at this diagram here, right, in this Penrose diagram where the central region is gravity and the side is flat, since its entanglement wedge ends up just being in the flat region with no gravity, we might as well do the computation just purely in the CFD2.
Right,
So,
that's what you did, but
yeah.
but now if I want to just check or for sanity reason,
okay.
and I say that if I compute SA complement, I should still get the same answer.
Yes.
So I'm
and
just
that will be
wondering.
true. That will be true because you see the entropy of PQ here, that would be the entropy literally of this PQ, but with this region being gravitational, the region between P and Q being gravitational.
Exactly. So now so how do I compute in gravitational?
Yeah.
So
the
now
way
we'll have
you
to use
can, yeah.
So probably now I'll have to compute the extremal surface in this ADS region and then see that it's same as this.
No, you don't have to, because what you have to realize that in 2D, the entanglement entropy of this interval is basically given by some 2-point function of some twist operators. So, you have a twist operator at P and a twist operator at Q. And the points PQ are still in a completely non-gravitational region. So the correlation function is like not affected by anything you do.
Yes, but A complement has SYK, and if I want to check now that SA complement is equal to SA that you compute, and SA complement we should get the same answer, but SA complement, to compute that, we would need the gravitational region, right?
Yeah, maybe what you're asking is, how do you know that there are no islands at early times, right? That's an equivalent way to say it. Because
yes, exactly.
Yeah, right. So the original problem we started with is a gravitational problem. And what you're asking is, okay, how do I know that there is no island immediately at early times?
I think that would be the equivalent rephrasing of the
That's
question,
an equivalent rephrasing of the state. Yeah. And we had some arguments in our paper that we wrote with Ahmed and Juan why it doesn't dominate at early times. And you can make some arguments based on entropy inequalities and so on, if I remember correctly. But I feel that it's also matches our intuition. I don't think we had a rigorous proof. We had some hand-wavy arguments, but it matches with the intuition that at early times, the linear answer is the correct answer. But if you ask me, okay, do we have a rigorous proof that there is no dominating island? I would say maybe we have a rough argument, but not maybe a rigorous one.
Okay.
I think that's true for any of these computations, even in an evaporating black hole. Unless you are in a very simple, for example, you can ask, is there a island like, having 2 disconnected regions so that you're computing some 6-point function in the CFT or something like that. You have multi-frag and all those, like you just say, okay, let me just look at the simplest possible thing. And
but I thought, see, because here this SA was the way you did the computation is exact computation, right?
Yeah.
And then we expect SA is equal to SA complement. So there should be not a question of estimation, but I think should be able to compute SA complement using gravity and show that this is really equal to SA the way you computed so far.
Yeah, and what I'm saying is that in the absence of an island in the SA complement computation, this would be the computation, right?
Oh, I see. Mm-hmm.
This would be the exact computation you would use up to the point of existence of some island.
Okay. Yeah. I see what you're saying. Yeah.
Okay. Thanks for the question.
Yeah. Thanks.
Okay. All right. So that that sort of completes the phase 1 of the system. I think we won't get to the phase 2 today because I haven't still told you what the JT gravity solution at finite temperature looks like. So JT gravity, because now we are not just in phase 1, we have to deal with the gravity solution. We have to say what the profile of the dilaton is and so on. So at non-zero temperature. And since we are at a finite temperature eternal state, we can look at first the Euclidean solution. Remember that the equation of motion that we got by varying the dilaton was r plus 2 equals 0. So it's ADS2 Euclidean. That means it's either the upper hyperbolic plane or the disk. And the relevant geometry for non-zero temperatures is the disk in global coordinates. So we have the metric ds square is d rho square plus sinh rho square d theta square. So this is like a disk where rho is the proper distance from the center, theta is the angle. Just a hyperbolic disk. Okay, and what was the equation for the dilaton? We also have to find what's the dilaton. Okay, the equation for the dilaton was del square phi GAB minus del A del B phi minus or plus minus phi times GAB equals 0. This was the equation. And if you look at the, again, the rho equation of this, it would be a first order equation. And what you would have is phi prime over phi equals sinh rho over cos rho. Actually, you can see this more directly if I was doing this and I found it simple. If we take the trace of the dilaton equation, then we get 2 grad square phi minus grad square phi minus 2 phi equals 0. So that says that grad square phi equals 2 phi. And now plug back into star. Plug into star. So there's a grad square phi here and the 2 phi here. So you get an equation grad A grad B phi equals phi times GAB. And you can see that if you just want to have a function phi, which is a function of rho, and then in this form of the equation, the theta theta component, the second derivative will go away just because it will be d theta squared phi is 0. And then the only term that contributes in this covariant derivative is the Christoffel symbol term, partial c phi equals phi times g theta theta. And then you can compute this. This is a first order equation. And the equation you get is this here. Just because g theta theta. So this thing involves the rho derivative of g theta theta. And this is g theta theta, which is sinh of rho square. So you can see how such a sinh rho over cos rho will arrive. But the point is there's a simple solution of this, which is phi equals a times cos rho. That just solves this equation. And that's our dilaton profile. So let's write it here again. ds square is d rho square plus sinh rho square d theta square. And phi is a times cos rho. Okay, now we want to go to the Lorentzian solution from this. This is the Euclidean solution. And also we've been writing our metrics in a conformal form, like with the omega square and the overall flat metric, which is not in this form. So we do the following: sinh rho square d rho over sinh rho square plus d theta square. And this is simple to solve if we define a new coordinate by d rho over sinh rho equals dy, then what you can show is that sinh rho is minus 1 over sinh y. And we will take y to go from negative infinity to 0. So we will take y to be negative. And rho, of course, goes from 0 to infinity. So this is just a change of coordinates. And with that, the metric becomes, so there's a sinh rho squared outside. But sinh rho is 1 over sinh y. So we get 1 over sinh y square times dy square plus d theta square. And now we go to Lorentzian signature, just analytically continue theta. Dy square minus dt square. And this is like minus dy plus dy minus. And so this is our conformal factor. So what we learned is that omega is sinh of y. And I was working all the time in the units when beta is 2 pi. But if you do put the beta back, you get sinh of 2 pi. Actually, minus y, because y was taken to be negative, because y is negative. So it's 2 pi negative y over beta times beta over 2 pi. So we have our omega, and phi is a times cosh rho, but that in terms of y is cosh y over sinh y. Again with a minus sign, just to keep everything positive. Okay, so this is our solution. So we have a new solution, and y is nice. Like, why is the y coordinate nice? Because you see, it makes the relation to 0 temperature easier. Y equals 0 is the boundary. So y equals 0 is the boundary. And we can see then that the metric is like 1 over y square near the boundary. It's just like the Poincaré metric. And similarly, the dilaton. Coth of y near y equals 0 is like 1 over y, which is what we had before. So we pick this y coordinate because it makes the near boundary behavior very similar to the 0 temperature solution. Okay, so let me just summarize here. So we have omega, sorry, let me write here, ds square is minus omega to the minus 2 dy plus dy minus, where omega is beta 2 pi sinh 2 pi negative y over beta. Phi equals phi r. Now I've just renamed the constant 2 pi over beta coth of 2 pi over beta times minus y. Earlier, this was just omega equals negative y, and phi equals phi r over negative y. This was the t equal to 0 solutions. So now we just have put some trigonometric functions up front. Okay. And we can also now compute the entropy of this black hole. What's the entropy? The Bekenstein-Hawking entropy of the black hole, right? We saw it's the value of the dilaton at the horizon. Where is the horizon? Horizon was earlier was at rho equal to 0, right? But here it's at y equals negative infinity. Y equals 0 is the boundary. So we just have the dilaton here. Coth at y equals minus infinity is 1. So we just get phi r times 2 pi over beta. But we should add the topological term, the phi naught. Remember, the JT gravity action has a overall phi naught. It's like minus phi naught chi plus phi times r plus 2, blah, blah. So this does contribute to the entropy. So what does this look like? So there's a constant term, it's phi naught. We should imagine phi naught to be big. And then it's just 2 pi times linear in temperature, 1 over beta's temperature. So if you think of JT gravity as coming from the dimensional reduction of some higher dimensional extremal black hole, This is like the extremal entropy. Extreme entropy of the extremal black hole, and you have here something which is linear in temperature. Now this is quite universal for near extremal black holes, that its entropy is a constant plus something linear in temperature. Okay.
I'm sorry.
Does it?
Yes.
Yes.
I think I missed some simple point earlier in
Yes.
the beginning.
Yes.
That
Cool.
that you started with the finite temperature. You said the solution is this.
Yeah.
How did you reason? What was the reason for that? For the metric.
Yeah. So the reason starts here at the hyperbolic disk, right?
Yeah, exactly.
We know
so
that. Yeah.
The reason
Any
for,
black hole geometry in a Euclidean space looks like a disk, right? So rho equals 0 here is the horizon. So maybe ask your question differently, or
okay, maybe let me try to answer myself. Is the idea that you first, the whole idea is to first start with the Euclidean, because there you know that by the normal technique of the time circle
exactly
things, and becomes at rho is equal to 0 becomes beta
exactly
so that was a trick. You started with the Euclidean and then found out the Lorentzian. Is that
exactly.
Okay.
So near the origin, so near the horizon,
I see.
rho equals 0. This metric looks just like d rho square plus rho square d theta square. And so the periodicity of theta sets the temperature here. So you could put some betas and stuff in this formula. I was working with a temperature beta equals 2 pi. And that's what I restored below. Like I restored the factors of 2 pi over beta in this thing right here.
Okay. Yeah, thanks. But could you write down the solution directly in the Lorentzian case? How would, or what?
Yeah, you could. Basically the Rindler metric of ADS2 is known, right? You essentially just need to write down the ADS2 metric and ADS Rindler coordinates. And it would be this.
Exactly.
Well,
Okay.
Usually people don't write it in the conformal form, but if you put it in the conformal form, this is basically the ADS2 Rindler metric.
Yeah.
What's really different about the solution, right? Because ADS JT gravity, locally everything is ADS2. So it doesn't matter what form you write the metric. This y is just some different coordinate.
Mm-hmm.
What's really different is the dilaton, right? In terms of the Pfefferman-Graham coordinate y, now it has a different profile. Instead of just being 1 over y, it's cos of y. And that's the real difference. It's sort of, this is the, phi is what sets where the singularity is. So like in the Penrose diagram, I was drawing these singularities, right? Let me just draw it again. So we have ADS2, we have the Rindler patch, but absent the dilaton, the entire global ADS2 could also have been a solution. The point is, because of this cos of y, the dilaton goes to -infinity at some locus here. Well, that's what makes the solution different. At this phi goes to -infinity. So it's really the profile of the dilaton and the boundary conditions that determine, the physical properties of the solution.
Gotcha. Thanks.
Okay. Other questions? Okay. Yeah, I'm afraid I've lost people. I don't know what to.
So is it the Lorentzian? Are you considering it? You are considering Lorentzian, not the Euclidean, or I mean.
Yeah, because eventually we want to compute the entropy as a function of time, right? So we have some actual physical not evaporating black hole, but even a real-time evolution in this eternal black hole. Right, so that's why we want to have the Lorentzian solution and have the Penrose diagram and everything.
Okay.
Okay. Okay, all right, so let's just compute then, try to compute, work towards computation of the QES and the phase 2 of the page curve. Okay, so there is going to be a part of the computation first, which requires, so this is like some lemma or something, some auxiliary computation. We need the entropy of an interval at finite temperature in a CFT2. You might think we already did that before. It's basically the same computation, but the interval PQ will not be like one endpoint on the left and one endpoint on the right. So literally we have to do a computation which is similar to the previous one, but where the interval is purely on one side. It's just purely on one side. So we have some point P and we have some point Q here. And we want the entropy of PQ, just a static entropy. This feeds into the computation, so I need to do this first. Okay, so let me just do that. And maybe if people missed it, the previous computation, please ask the questions here because this is very similar. So we have the point P and we have the point Q. So remember Y was the Rindler coordinates, which cover, for example, this just the right patch here. And X are the Minkowski coordinates, which cover the big square here, the left, right, top, bottom square. Okay. All right, so coordinates of point P. The Rindler coordinates, that's just, we start by taking time 0 and position A. A point Q is time 0 and position B. We will only need when the points P and Q are on the same horizontal slice. Okay, so the light cone coordinates, Y plus and Y minus, is just T plus Y and T minus Y. And it's T plus Y and T minus Y here. And X plus and X minus, remember, X plus and X minus are exponentially related. In this quadrant, X plus is positive, so it's just e to the Y plus. And X minus is negative, so it has an overall minus sign, and then it has an e to the minus Y minus. Okay, so X plus is e to the A, and X minus is negative e to the A. Here, it's e to the B, and then it's negative e to the B. Okay, so we have the X plus and X minus coordinates of P and Q. But again, as before, we need to be careful about the Vial factor. So the metric is actually, we want to compute the entropy of some system in Rindler space on just the right side, where the metric is the flat metric in the Y coordinates. But since Y is log of X plus, we get this over X plus, and we have this over X minus with a minus sign. So again, we have an omega, which is negative X plus X minus to the 1/2. Okay. All right. So what is the entropy of PQ? It is C over 6 log of delta X plus C over 6 log of delta X minus minus c over 6 log of omega at p minus c over 6 log of omega at q. Okay, equals c over 6 log of. Okay, so now the x plus and x minus differences we read off from here. The delta x plus is e to the b minus e to the a, right? Times 2, because the x minus is the same difference. Minus c over 6 log. Now omega at p is the product of this and this raised to the 1/2. So that's e to the a, and minus c over 6 log of e to the b. Okay, so we can write this as c over 6 log of e to the b minus e to the a squared over e to the a, e to the b. Okay, and this is equal to c over 6 log of, let's see, minus 2 times e to the b minus a plus e to the a minus b, right? So that's equal to c over 6 log of 2 cosh b minus a minus 2, which is equal to c over 6 log of 4 sinh squared b minus a over 2, which we can write as restoring factors of beta c over 3 log of sinh b minus a over 2 pi over beta times here beta over pi, right? Because this formula was for beta equals 2 pi, and beta has dimensions of length, so b minus a, and then there is this 1 over beta here. Okay, and notice that in the limit when beta goes to infinity, which is the 0 temperature limit, you recover the previous formula. You recover log of b minus a when beta goes to infinity. And you might have seen this, that finite temperature entropy in flat space in a CFD2 is simply related via conformal transformation to the 0 temperature thing. And this is basically what we have done. The conformal transformation is this one. So what we have computed is the entropy of an interval in a CFD2 on R1 at temperature beta of an interval, S of an interval between coordinates A and B, between A and B.
So inside the log, beta is a dimension-full parameter.
Sorry?
So in the inside of the log, the argument of the log, beta is a dimension-full. So you would need some other like a dimension-full.
Yeah, there is the UV cutoff.
UV cutoff, I see.
Yeah, because as beta goes to infinity, we need this to go to c over 3 log of b minus a over epsilon. So there's like some epsilon here.
Okay, thank you.
Yeah, this result is of independent interest, just for. Okay, what we'll do is maybe we will stop here, and next time we will use this result together with the finite temperature solution that we have written down to write down the generalized entropy functional and extremize it and find the island and compute its entropy and get the flat part. It's just algebra from here. But I want to emphasize maybe this computation, because all you have to do is you have to keep the plus and the minus straight. Like and then just follow through. There's a simple algorithm. There's a simple formula for the entropy. You have to make sure you keep the Vial factor correct. And that's it. Like, you land on your feet, you get the right answer. There's no magic in this story. Look, the algebra is very simple. Like, even this 2D gravity theory, like, is just a bunch of trigonometric functions. And this equation for the JT gravity is not that hard. Like, this is the most complicated equation. And that's also sort of reduces to a first order equation, which is easily solvable. But what's difficult about this business is so many things going on in parallel. Like, you have to just keep the physics in sight. There's a gravity solution, there's a finite temperature, conformal transformations, and all that. And that you just have to just do all the steps carefully. Okay, thanks. I'll stop here.
Thank you very much. Very clear explanation. And please ask any question.
Yeah.
This might be
Yes.
maybe a stupid question. Why do you start with thermophile double? Can we do with that?
Yeah, it's just that we want to be, the goal of this is to come up with the simplest situation, the simplest scenario to see the page curve. And the point is the thermophile double allows us to do that, because we have intuition from Hartman-Maldacena that thermophile double is like a quench state for forwards time evolution on both sides. And yeah, that's the reason. There's no, like, these people discovered, these islands and non-trivial quantum extremal surfaces in other situations as well, just like an evaporating black hole. But it's just, the algebra is very simple. Like, as I will show you next time, like, there's just some log of a sinh function here and some, cinches and coshs here. And that is enough to see this physics. So what you really buy by going to this thermophile double setup is simplicity, while keeping all the physics in place. Like, if you look at the Almeri, Engelhardt, Marolf, and Maxfield paper, in which they do real-time evolution of an actual evaporating black hole, math is a lot more complicated.
Right, thanks.
Yeah.
Also, it is similar to what I asked before. So usually this entanglement calculation is done in the usually done in the Euclidean, and here you just using that Euclidean result, and you assume it, you consider it to be analytic continuated. Is it?
Oh, you mean this computation of the entropy that I did here?
Yeah, usually like a twist and inserting twist operator
Yeah.
and so on is done in the, I guess, in Euclidean.
Yeah.
So
Yeah,
here you
but
just use it in the like a Lorentzian version of it.
yeah, like the entropy that I computed, if I just was to not draw time, but there is some infinite space, and there is some hot gas everywhere. That's what it means to be at finite temperature, right? This is our system. It's just a one-dimensional system with a bunch of hot gas. It's static. And we are just computing the entropy of this interval here, right? AB. And that's the computation we are doing. So because the situation is static, there is a Euclidean computation available. And what I used I used a result which was derived from Euclidean methods, like the correlation function of twist operators and so on. But we might have as well have said, okay, it's a correlation function in Lorentzian time, because even the correlation functions in Euclidean and Lorentzian time analytically continue to each other. Right. But this is really the physical setup, and this is the y direction, which is infinite. So what we do via this this doubling trick is we perform a conformal transformation. We have a dy plus dy minus. We divide by y plus so as to bring this point at minus infinity to a finite location.
Yes.
So we sort of compress it, right? So we compress this line and bring in its partner from the other side, like its purifying partner, and glue it here. And then that sort of creates the Rindler horizons. So this hot gas in the y line on the infinite line R, it becomes this pure state on the x line, right?
Okay. Yes.
So there's a pure state on the x line, but if you just looked at the right system, it's like a hot gas on the infinite y plane. So this is really this Bisognano-Wichmann theorem or whatever. So this is the physical system, and it sort of lives just here. But in order to be able to glue something from the other side, you need to bring this point at the origin to a finite distance, from the bulk of the system. So that's why you need the conformal transformation, which affects distances, brings minus infinity to a finite place, and then you glue in the purification on the other side.
Okay, thank you.
Okay.
Any other question?
Okay, that's fine. Maybe we can.
Yeah,
we can.
Yeah, let's thanks speaker again.
Okay, thanks a lot, guys.